Recall that the naive Bayes algorithm fundamentally uses this particular mathematical theorem called Bayes theorem. That's where the word Bayes comes into the algorithm. The name is naive Bayes. Sometimes it's also called idiot Bayes because it's the simplest kind of classification algorithm, and it's not as sophisticated as, say, support vector machine based classification. Uh, but having said that, it doesn't work that bad. It's just that it's not the best possible algorithm, but it does work reasonably well. So it's maybe this name is a little it may be a little misleading. Of course, it depends on the context. In some contexts, naive Bayes may not work well. So this is Bayes theorem, and if you recall, the way so there are two versions of naive Bayes algorithm, and we looked at one of them. And the idea is that in the training phase, as you are parsing each document that you are shown with the particular class label, you keep noting which words appeared in the documents of a particular class. For each class, you note which terms appeared in the documents that are present in the documents that are associated with that class. So you can prepare that list of words or terms which appear in those documents, as well as how many documents those words appeared in. Okay, and based on that, you can calculate the probability of a particular word W appearing in a particular class C. Okay, so what is the probability that word W appeared in a document of class C in the training phase? This would just be the total number of documents that had the word W, number of documents that had the word W in it, divided by the total number of documents in the class C. The total number of documents associated or labeled with class C. So obviously these documents that we are looking at for the presence of word W are documents out of these. So we're not looking at all documents having the word W. We're looking at documents associated with the class C which have the word W in them. So you compute these probabilities for every word in your vocabulary. Okay, so compute these for every word W in the vocabulary and for every class C. So you can imagine having a table where for each class and for each vocabulary word or vocabulary term, you have a number indicating how many so for a particular word W and for a particular class C, you will have a number denoting how many times the word W appeared in documents of class C. Okay, so one thing that you have to note here is we are only looking at presence or absence of W. Okay, we are not looking at in a particular document. We are not looking at how many times the word W appeared in those documents. So we are not looking at term frequencies. Okay, we are just keeping track of presence or absence. And then based on what this particular frequency is, it's like a document frequency, except that we are just focusing on documents labeled with with the class C. So the number of documents having the word W in it divided by the total number of documents that are labeled with class C. So you can either directly store the probability here, or you can compute it on the fly. I mean, the implementation is separate, but conceptually this is what you're doing. Now, what happens when a new document comes in? So when a new document comes in, let's say that the new document has words W1 to WK in it, okay? And well, actually, let me call, yeah, I can call them as W1 to WK. But let's say that the total number of words in the vocabulary is the size of the set V. So if V is this vocabulary set, the vocabulary itself may have many more words than the words in this document. Okay, so K will be much smaller than the size of the vocabulary in general. So what would you do? How would you compute the probability that, so firstly, how would you classify, what's the overall problem? You have to classify this new test document D into one of those, into one of the classes. So let's say there are J classes. So you will compute for each class C. Okay, so for each class C, you would compute the probability that this particular document, that given this document, it falls into the class C. And for this, you would use Bayes theorem. Okay, so given this document D, what is the probability that it falls into class C? That's given by the right hand side. So this would be the probability that given the class C, you're going to see a document. So let's not worry about what exactly this, but of course you can see directly um, from the name itself that this is the probability that given that you are from class, given that the document is from class C, what is the probability that you will see these K words? That you will see a document having these exact K words in it. Okay, so actually maybe I should denote it as, so this, think of replacing this D with this particular vector. Okay, so these are the K words that appear in D. So given that the document is from class C, what is the probability that it will have the K words W1 to WK in it, multiplied by the probability of C divided by the probability of the document. Okay, so given the document having these K words, what is the probability that it falls into class C? That's given by the right hand side here. Now we don't have to actually compute all the three terms here, because we have to compute this value for every class C, but more important than the absolute value are the relative values of these probabilities. Which of them is the largest? Whichever value of the probability is the largest, that is the class into which this particular document falls, because that is the class that is most likely given this particular document. So the denominator on the right hand side is going to remain the same for all the classes. And so we can ignore the denominator, we just look at the numerator. This is the prior probability of seeing a document from class C based on what is the frequency with which class C appeared in the training phase. And this is the probability that if you are given a document from class C, these will be the K words. Now the naive assumption in naive Bayes was the assumption that the probability of seeing these keywords can be written as the product of the individual probabilities. That is, the occurrence of these keywords in documents of class C is independent of one another. So these are all independent occurrences of, these are all independent events. And we saw that even though this assumption is not strictly true, what matters here is the accuracy of the classification, not really the accuracy of the estimation of this particular value. As long as the inaccuracy in the estimation does not lead to a mixing up of or a change in the classification results, it's okay to, make this naive assumption. And that's what it turns out to be the case. This naive assumption does not generally affect the classification accuracy that much. It does not change the classification that much compared to what we would have obtained had we had a way to directly estimate the probability of seeing these keywords given a document of class C. Now that probability is difficult to estimate directly because you need a huge number of training examples of documents from class C so that you are able to see a sufficient number of documents that have exactly these keywords in them. Okay, so this is how we did it. Now there's a slight difference between what I just described and the way this particular version of naive Bayes works. You're not only multiplying the probabilities that W1 to Wk are present, you're also multiplying the probabilities that the other words, that is the words in this vocabulary set other than these keywords, are absent. Okay, so if I call those words as say A1 to I don't know, AL. So what is the probability of not seeing A1 in class C, in a document of class C, multiplied by the probability of not seeing the word A2 in class C, and so on, okay, up to AL. So this obviously would be just 1 minus the probability of seeing A1, seeing the word A1 in a random document of class C. Okay, so if you have done a course on probability, you know that there is something called a Bernoulli random variable. Okay, and it's a random variable which takes, so here's the Wikipedia page for it. It's a random variable whose probability of being 1 is p, and the probability of being 0 is just 1 minus p. Okay, or you can call it q and 1 minus q, doesn't matter. But this particular random variable here corresponds to the presence or absence of this word in the document. So if the word is present, if the probability of the word being present is p, the probability of the word being absent will be 1 minus p. So that's a Bernoulli random variable, and there are many variables here. Okay, this formula just doesn't have a single random variable. It has a random variable for each of the words in the vocabulary. Okay.
Wait, sir, around when you are saying what P and Q are on that part.
Okay. Yeah, so a Bernoulli random variable is just a random variable whose probability of being 1 is p, and the probability of being 0 is 1 minus p. So it can take only two values, 0 and 1. If it takes a value of 0 with the probability of p, then it takes a value of 1 with the probability of 1 minus p. So each of these events, each of these events of seeing a particular word in a particular class or not seeing a particular word in a particular class can be looked at as a Bernoulli random variable, because either either this particular word W1 will be present in the class C or it will be not present in the class C. So if it's present in the class C with a probability of P, it will be absent in the class C with a probability of 1 minus P. So what I explained here was that the probability of, if you're given a random document from the class C, the probability that this random document will have exactly these keywords W1 to WK is the product of all these random variables, P of W1 given C, P of W2 given C, and so on till P of WK given C, multiplied by the probability of the absence of all these other of all these other words from that document. So the words other than W1 to WK in your vocabulary are denoted as A1 to AL. And we are saying that the probability of seeing exactly this set of words is the probability that each word in this set is present and the probability that each word that's not in this set is absent. So there are a bunch of Bernoulli random variables over here. So that is why this is called a multivariable or sometimes a multivariate Bernoulli model. Okay, so naive Bayes has two versions. The first version is called the multivariate Bernoulli version of naive Bayes, because the model, the probability model that's being used here is the multivariate, is the Bernoulli model, and there are multiple variables, and so you have a multivariate Bernoulli model.